Alright, now we know how to visualize relationship between two variables via scatter plots, and also we know how to measure the strength of this relationship by using covariance. However, covariance has one important drawback. It depends on units. You remember that covariance is when you take distance for x and distance for y and then multiply to each other, and that kind of makes no sense, because if this is kilograms and this is meters, you multiply meters to kilograms. If this is centimeters, you multiply kilograms to centimeters. So the outcome, the result of your calculations will highly depend on the units. Let me show you an example. So here I have people. The x is height. In this case, you can see it's in centimeters. The y is weight in kilograms, right? And this is the overall covariance. It's 170, which looks like a big number. And indeed, you have a very nice, strong linear relationship here. This is another plot. You can see that actually it's the same data. If you look at the points, they have the same behavior, and the relationship is the same. It's as strong as the previous one because it's identically the same data. The only difference is that here height is measured in meters, so I just use another unit. I didn't change relationship between variables. However, covariance is 100 times smaller. Why? Because meter is 100 times smaller than centimeters, I mean in units, right? For 100 centimeter, it's 1 meter. So therefore, covariance is 100 times smaller, but it doesn't mean that the relationship is less strong. So it just shows the drawback of the covariance. So covariance highly depends on units. Okay. So we need to solve this problem. We need to find a better covariance which will not depend on units, and that's what we are going to talk about now. First of all, we already know how to get rid of units. We need to standardize the values. You remember that what we discussed in block number 1 in normal distribution. So if your values follow normal distribution, you can standardize them by subtracting the average and divide it to standard deviation. If you know population parameters, you can do it with population parameters. If you don't, then you can use sample estimates of your population parameters, right? So in this case, you get, instead of x, you will get a new variable z, which is a standard score. So it tells you how many standard deviations your value x is from the mean. And if you do it for every variable, you will get the same units, because every variable, every z-score will be represented as a number of standard deviations. So you solve the problem of units. Now let's try to do this for the covariance, right? So this is our original covariance. So the idea is that we need to standardize these values. We need to use zx and zy, so the z-scores. But remember, what is z-score? For x, for example, it's x minus mx divided to standard deviation of x. For y, it will be x minus my divided to standard deviation of y. But you already have x minus mx. So what you need to complete the standardization is just to divide to standard deviation of x and standard deviation of y. Let's do that. This new statistic we will call R, and you already see the name, right? It's a correlation. So correlation is when you take a covariance, but you standardize your values first. So you can see I standardize the values first. But because neither standard deviation of x nor standard deviation of y, they do not change inside the sum, right? They're constant. We can put them outside the sum, right? And if we do that, that's what we got. But look, what is this? This is exactly the covariance. So it means that the correlation is simply standardized covariance. So you calculate covariance first, and then divide to standard deviation of x, standard deviation of y. So that's what the meaning of correlation is. Or strictly speaking, correlation, it has two meanings, this word. It's a property of two variables to relate, but also it's a statistic. But in order to avoid confusion, sometimes we call it correlation coefficient or coefficient of correlation. So coefficient of correlation, it's standardized covariance. However, you can also recall how we got this, right? So we compute, the idea is to replace this with z-scores, right? So in fact, you can compute covariance for z-scores, and the result will be identical, of course, because that's exactly what you have here. This is zx, and this is zy, right? And correlation is simply a covariance computed for z-scores. So on other side, correlation, it's a covariance of standardized values. It doesn't matter how you calculate it. Calculate covariance first and standardize it, or calculate z-score and then compute covariance, the result will be always the same. So correlation is simply covariance computed for standardized values. You get rid of units, you get rid of problem with scales, and that makes it universal, versatile measure. Okay. Now let's get back to our initial example. You remember that I tried different pairs of variables from the people data. And then we discussed that, okay, we can actually see some linear trends in most of them, right? So we have two statistics that helps us to measure this linear trend, it's covariance and correlation. Let me show you these statistics here. So you can see this is correlation for the first case. So this is covariance and this is correlation. And this is, for example, covariance and correlation for the second case. Look how huge covariance is. So covariance here is much larger than covariance here. But we know it's because of the units. Here we have euros. And people learn a lot of euros, right? It's not just 1 or 2 euro, it's usually like 40, 30 euros, 1,000 euros per year. So that's why the covariance is huge. But if you compute correlation, you can see this number is smaller than this number. This is 0.96. It's smaller than this number. So it shows indeed that this trend is weaker than this trend, right? Why? Because you can see the points are kind of scattered around this line, while the points are much closer here to the line that we actually made here. So the closer points to the line, the more strong this linear trend is. And correlation clearly shows you that. For example, here the correlation is minus 0.65. First of all, you can see minus, so it indicates that trend is negative. And then you can see it's not as strong as this one or as this one, so it's weaker because points are more scattered around this line. Finally, if you look at these, you can see the correlation is 0, which confirms that indeed we don't see any clear trend here. We don't see any clear relationship here. So correlation is a universal measure of linear relationship between two variables, regardless which units these two variables have. Okay. Well, because of this standardization, the correlation values are always limited. So correlation cannot go beyond -1 and +1. It can be proven mathematically. And it will be -1 exactly if points align on a straight line with negative slope. It will be +1 exactly if points align on a straight line with positive slope. If points are absolutely chaotically scattered, the correlation is 0. Okay. So in both cases, if it's -1 or +1, it's a strong correlation because the points have a very clear, very strong linear trend. They line exactly on a straight line. Okay. Sometimes people also use adjectives to define how strong the correlation is. And this is the table, right? So if correlation is above 0.9, it's called very strong correlation. If it's between 0.7 and 0.9, it's strong. Then you have moderate, you have weak, and you have correlation 0. But use it with caution because what is strong in one area of science can be not very strong in the other area of science. It depends on how big the noise is, how big the random variation is. So therefore, please use it with care. Okay. Then this is just examples to show how it feels like to have a high or low correlation. For example, in this case, you can see it's almost 1, and indeed points aligning almost exactly on a straight line. The variation is very, very little. Here you have almost -1, and indeed you can see the points align almost exactly on a straight line with negative slope. So remember, negative means when one variable goes up, second variable goes down, right? So in this case, you can see the variation is very low, almost exactly on a straight line. So therefore, the correlation is close to 1 and -1. Here you have a strong correlation, but with a higher scattering. Here you have also a quite strong correlation. This is very strong. This is strong correlation, but you can see it's a little bit weaker, especially in this case, it's a bit weaker, right? The drawback of correlation is it can be computed for two variables at the time. And for example, we have 12 variables here. So how many pairs we can make? Well, I can tell you 12 times 11 divided to 2. That's the number of pairs you can make, and that gives you 66 pairs. So you can compute 66 unique correlation coefficients. And that will take a lot of time to compute it pairwise, right? So usually instead of computing this pairwise one by one, we compute a correlation matrix that looks like this. So you can see that in this case we have a matrix 12 by 12, right? So it's 144 values. This is diagonal. Diagonal is always 1 because it's a correlation between the variable in itself. For example, this is IQ and IQ, right? So this is 1, right? And then you can see that this matrix is symmetric. What you have on the upper corner, right corner, it's the same as the left bottom corner, right? And the idea is very simple. For example, let's take income. You can see these are all correlations for income. So this is correlation with height, with weight, with hair length, with shoe size, and this is with age. Remember, that's what the plot that we make. It's a correlation with age, and then the correlation with other variables, right? Of course, it's a lot of numbers, and the representation of correlation matrix in the numeric way, it's not very obvious where the patterns are, which variables highly correlate, which variables not highly correlate, and so on and so forth. So therefore, when you have this kind of correlation matrix, it's better to visualize it. And what we visualize it using a heat map. What is a heat map? You simply replace every value here with a colored square, and the color of the square depends on the correlation coefficient. For example, here you can see this is the color scale I use. So if it's yellow or yellowish, it's 0, and then the more reddish it can become, the higher positive correlation you have. The more bluish it become, the more negative correlation is it. Then you can clearly see patterns, right? So for example, you can see a very large pattern here, in this case, right? So these all variables are highly correlated with each other. It's swimming ability, weight, height, shoe size, and so on and so forth. You have a pattern here, you have a pattern here, you have a pattern here. These two variables are negatively correlated with this big cluster, and so on and so forth. So this heat map gives you a very clear idea of any cluster, so any variables that correlate with each other. I'll show you how to make this cluster in R in the last video of this learning sequence. Meanwhile, just keep in mind that it is possible. So this is what correlation is, coefficient of correlation is. However, you remember that if you compute correlation coefficient for your sample, it's a random number, right? So if you take another sample, it will be a new number. If you take another sample, it will be a new number, and so on and so forth. So we need to learn how to make an inference, how to compute, for example, confidence interval for correlation. And that's what we are going to talk about in the next video.